All right, thanks for coming to the review session today. So I was going to start with questions that people sent me in advance, and nobody sent me any advanced questions. So we'll just go with kind of starting with what questions you have. So I did want to just show you, make you aware first. That if you go to the exam prep area here, this exam prep guide does tell you kind of what's going on. It is a semester old, but the format is exactly the same. So in total, there will be 22 questions on the exam. 16 of them will be multiple choice. The other 6 will be some combination of either short answer or calculation. There will be some nomenclature questions on there. So just like what you saw in the proficiency, you need to be able to name from formula or derive formula from name for a number of compounds. They could be acids, they could be covalent compounds, they could be ionic compounds. It's going to be a mixture of those three. So think back to how you prepared for those proficiencies when you're preparing for this part of the exam. So it's not a big part, only 9%, but it is something that you should be able to get relatively easily if you have a handle on those concepts already. About a quarter of the exam is from chapter 7. So in there, we're looking at balancing equations, being able to do things like predicting products, identifying single replacement, double replacement, combustion, that kind of stuff, as well as doing these 3 main calculation concepts: stoichiometry, identifying limiting reactants, or doing theoretical and percent yield kinds of problems. So these kinds of questions, those might show up on the latter part of the exam, that short answer calculation part, because that's going to be that kind of question. I generally don't do calculation kinds of questions in the multiple choice because I want to see your thought process. And it's a lot easier to kind of mark where you're going wrong, or, you know, if you were on the right track, if your work is kind of laid out in front of me, as opposed to you chose C instead of A. But the bulk of this exam, as you might expect, is in that chapter 8 part. And the primary reason for that is that's where we spent the majority of the time over this past 3 or so weeks. So what do you need to know how to do? You need to know how to calculate concentration. In particular, you need to know how to calculate molarity. You need to know how to calculate mass percent, parts per million, parts per billion. You need to be able to do dilution kinds of calculations. You need to be able to identify electrolytes. And so a lot of that comes down to your knowledge of the solubility rules, because strong electrolytes would be in the category of strong acid, strong base, or soluble salt. Weak electrolytes would be in the category of weak acid or weak base. And non-electrolytes would either be things that are insoluble or things that are molecular, like water or ethanol or sugar. You need to know something about Bronsted theory, which is that showed up on the Chapter 8 quiz, knowing the difference between identifying an acid based on its formula versus identifying an acid based upon its action. Identifying it based on its formula, that's something called Arrhenius theory. And it's really good for identifying kind of acids in a vacuum. But if they participate in a chemical reaction, that acid better be ditching a hydrogen. And if it's not, then it's not an acid. If it's gaining a hydrogen, it's a base. And then finally, looking at things like ionic equations. Being able to break a molecular equation down into an ionic and a net ionic equation. Being able to do redox, identifying oxidation numbers, monitoring how those oxidation numbers change, and identifying, okay, this was oxidized, this was reduced, this was the oxidizing agent, this is the reducing agent. And then the last part, the part where I came in, the titrations, solution stoichiometry, being able to apply those concepts of concentration to stoichiometry chemical reaction systems. And so those are the topics. You could see any number of those topics showing up tomorrow. You're not going to see all of them. I can guarantee you that. That test would be about 2.5 hours long. But you will see a number of them. And what I often like to do to save us space is I will often integrate concepts into a problem. And so what I mean by that is instead of having a separate question where you balance a chemical equation, I might have you do a limiting reactant problem where the first thing that you have to do is balance the equation. And then identify the limiting reactant. And then calculate the percent yield. And so one question addresses 3 or 4 of the concepts on that list. It might be the only time you see one of those concepts, but it's still touched on somewhere there. So don't expect a big long section for each one of these. Some of them are literally just going to be touchstone kinds of things where I'm going to present this in the context of something bigger. And can you connect the dots? So like I said, my exams tend to be on the more challenging side of things, not because I'm trying to fail you or I've got it out for you, but I really want to see who is good at kind of using the chemistry and connecting concepts, and who is good at identifying equations and just kind of plugging and chugging. The first kind of student is the one I'm trying to get you to be. The second kind of student will get by, but they're going to be scratching their head at different parts of the time during the course of the exam. So that's just kind of an overview. Now, as far as the equation sheet, you will get an equation sheet just like you have for all of your quizzes. You'll also get a periodic table, just like you have for every quiz as well. So you don't need to twist yourself up too much trying to remember what the titration equation is. It's right there. All right, any questions about that before we look at the practice test? All right, so now I'm going to turn over the review to you. Hopefully you were able to look at this prep test a little bit and you can kind of bring to the table some of the things that you're struggling with a little bit. So I'll open up to whoever wants to go first. Sure. So this is out of the short answer section, right? Okay. Well, to answer 5B, we have to answer 5A. So let's go ahead and look at both then here. So the question in front of us, we have a 12.36 gram sample of copper metal. It requires 18.92 milliliters of nitric acid to react fully. And the first part is balancing the equation. The second part is actually determining that concentration. And so from a balancing standpoint, this is not your easiest of equations to balance, but it does eventually work out. I believe you need a 3 here. No. Oh, you know what that. All right, so this is coming back to me now, I believe. Oops. That is the wrong key. That's very wrong. Of our. Well, okay. I think I just had my files mixed up here. I think for the most part, I've got it here. The key will post after the review session. So yeah, that was the. So to balance this, I need 4 nitric acids and 2 nitrogen dioxides and 2 waters. So this is kind of the opposite of the case what we saw in lecture. In lecture, we were using molarity to get us 2 moles, and then we did the stoichiometry to kind of figure out the rest. Here, it's the opposite. We're going to use stoichiometry to figure out the number of moles of nitric acid, and then divide it by the volume to get the molarity. So to figure out the number of moles of nitric acid, I need to take that 12.36 grams of copper and there are 63.55 grams of copper in every mole. And our ratio here, 1 mole of copper for every 4 moles of nitric acid. So our grams cancel, our moles cancel. We're left with moles of nitric acid, 12.36 times 4, divided by 63.55 to 4 significant figures. We give us 0.7780 moles of nitric acid. To turn that into concentration, remember, it would be moles of nitric over liters of solution. So moles, 0.7780. 18.92 milliliters is 0.01892 liters. And so this would come out to be 41.12 molar nitric acid, which is like 2.5 times, the limit of how concentrated nitric can actually get. But so that's the process that you'd have to undergo, though. Use the stoichiometry to get you to moles, and then use your definition of molarity and take the number of moles that you calculated and divide it by the volume of the solution you were given. And so the trick I would always use for something like this is, if you don't know exactly where to go or what to do, kind of start with the conversions that you can make. I know I have a mass of copper. Well, I can turn that mass of copper into moles by dividing by the molar mass. I can turn the number of moles of copper into moles of nitric acid. And even if I go no further than that, I've at least showed some level of intuition that says that I didn't know exactly what to do, but I did something, and that something made sense. So again, this is all about kind of adding partial credit, trying to do things in such a way that even if you don't get the whole thing right, you at least showed that you had some idea of what you were doing, and you are able to get some credit for that. Okay. All right, that was good. Another question. Yeah, give me. Sure. So let's look at that in the context of question number 4, because question number 4 is going to kind of handle that concept along with some others. So question number 4 asks the question, here I've got the combustion of butane, C4H10. I've got 1,115 grams of butane. I'm reacting with 965 grams of oxygen. The first task is to balance the equation. To balance the equation, I'm going to need 2 butanes, 8 carbon dioxides, and 10 waters. If I put that together, 16 plus 10 is 26. So I need 13 oxygens as well. Now, how did I know to do it that way? It's a trick with combustion reactions. If you are dealing with a combustion reaction, of a hydrocarbon, take the number of carbons and double it. If you need 2 more after that, then you're also going to need to double the number of carbons. So if the number is even, that's what you do. If the number is odd, then you look at it a little bit differently. So if the number is odd, if you double it and you still need 2 more, it's fine. But in this case, I had 4 carbons in it, so I had to double the whole reaction. The next question concerns the limiting reactant. There are lots of ways to go about calculating limiting reactant. The way I go about it, the way I teach my students to go through it, is I'm going to take each of these reactants and I'm going to turn them into one of the products. Now, which product do I choose? It technically doesn't matter, but chances are pretty good I'm going to be asked about a yield question later on here. There it is, theoretical yield of water. So I'm going to convert these to water. And the reason I'm going to convert them to water is to save myself the additional calculations later of having to do the whole calculation process again. Because stoichiometry problems take a while to set up because you've got at least 2 or 3 conversions in each one. And so if I've got to do 3 conversions for each reactant here and 3 conversions to do the yield question later, it'd help if 3 of those conversions were the same conversions and I just need to write down my previous answer. So that's what I'm going to do. So butane, 4 times 12.01 plus 10 times 1.01 give us a molar mass of 58.14 grams. The mole ratio, 2 moles of butane for every 10 moles of water. And every mole of water weighs 18.02 grams. So put that all together, 1115 times 10 times 18.02 divided by 58.14 divided by 2. To 4 significant figures, I get 1,728 grams of water. Is that a lot? Seems like it, but we don't know in the context of the other reactants. We got to do the same thing for the oxygen. Oxygen, 16 each, so 32 grams for every mole. 13 moles of oxygen for every 10 moles of water. And every mole of water is 18.02 grams. So the one nice thing about these calculations is that there is some repeatability in them. 965 times 10 times 18.02 divide by 32, divide by 13. To three significant figures, it's 418 grams of water. So this result tells us two things. First of all, it tells us that the limiting reactant is oxygen, because oxygen made far less product than the butane did. The other thing it tells us is that the theoretical yield of water is 418 grams. Another important piece of information, since 2 questions down from here, it asks us exactly that. Okay, for part C, calculate the mass of the other reactant left over if the reaction goes to completion. Again, there are a lot of ways to calculate this, to do this problem. You could convert the 965 grams of oxygen back into butane, figure out how much butane gets used up, and subtract. That's one way to go. The way I tend to favor is, since I did all of this work here, I kind of figure it's a shame to waste it. So 1,728 grams of water. I'm going to subtract out the 418 grams of water that are actually made. And that gives me 1,310 grams of water that were excess. That excess, I can now convert backward to figure out how much butane would have been used to make it. And so all I'm really doing is taking this stoichiometry here and running it back. 18.02 grams of water for every mole. 10 moles of water for every 2 of butane. Every mole of butane weighs 58.14 grams. So if I do that, 1310 times 2 times 58.14 divided by 18.02 divide by 10 to 4 significant figures, 845.3 grams of butane are left over. Like I said, you could have gone a different direction with this. You could have taken your limiting reactant, converted it into a mass of butane, and done the subtraction of that mass from 1115. You would have come up with the same answer, essentially. Basically, all that you're doing in either case is you're doing a conversion step and you're doing a subtraction. The order of which you do it just depends upon the method you use. Question D asks for the theoretical yield of Water, we already did that. It's 418 grams. If you did not follow this process, just a couple of things that you have to remember. When we are calculating theoretical yields, we always have to start with the limiting reactant. And we take that mass of limiting reactant and convert it to the product that we're interested in. So since we did that above here, we don't have to replicate it. But if we didn't do this set of calculations first, then all we would do is just that, do the stoichiometry and figure out the calculated value. That's what theoretical means in this case. It means calculated. As opposed to this number here in part E, the actual yield or the experimental yield would be the result of what happens when we do this reaction in a real world scenario, in the laboratory, in the field, wherever. So this value is derived from experimentation. This value is derived from calculation. To get the percent yield is actual over theoretical times 100%. So 375.9 grams divided by 418 grams times 100%. To three significant figures, 375.9 divided by 418 will give us 89.9% yield. So I know that was kind of the long and drawn out way of getting to the overall answer to the question. But the reason I went through all of it was they all inform each other. Ultimately, to do percent yield, you need a theoretical yield and an actual yield. And so the actual yield was given to us. We had to calculate the theoretical. And with that theoretical yield, we could then calculate the percent. All right, so let's take a look at another question or another problem. Anybody got something? Okay. Okay. So I actually like this question a lot, so much so that when I started to design the oxidation numbers proficiency, I used this format. So if you're looking ahead a little bit, next Friday is our first attempt at the oxidation numbers proficiency. It's going to be very similar in format to this kind of question. You'll be given a chemical equation. You assign numbers to each of the elements in the equation. You identify the oxidizing agent. For now, though, let's just look at this problem at hand. When it comes to oxidation numbers, what we need to remember are kind of those basic guiding principles. Those are our common rules. And so the primary derivative off of those common rules is something I call the algebraic method. So when I'm trying to determine the oxidation number of these substances, the algebraic method is what I'm going to use. Sometimes it's very straightforward. So for carbon monoxide, carbon plus oxygen equals 0. If oxygen is -2, then carbon has to be +2 to match up that charge and get something neutral. Sometimes it requires just a little bit more work. Chlorine plus oxygen equals -1. Chlorine -2 equals -1. Chlorine must be +1. The oxygen is -2. But what I can see is that even in the more complex kinds of situations, carbonate, carbon plus 3 oxygens is equal to a -2 charge. If each oxygen is -2, carbon plus -6 equals -2. Carbon must be +4. And chlorine in this circumstance, since it is the only element in an uncharged molecule, 2 times chlorine equals 0. Chlorine must also be 0. So to answer the first question, is it redox? What we need to do is look at the charges themselves and answer a simple question. Do the charges change? And since they do, the answer to this question is yes. Now, if the charges did not change, that doesn't mean that it's not a chemical reaction. It just means that it's not a redox reaction. But since it is a redox reaction, then what we want to do is we need to identify the thing that is oxidized, the thing that is reduced, and in this case, the oxidizing agent and reducing agent. Now, of our elements, I can see that the oxygen did not change. So from a standpoint of trying to figure out what was oxidized and reduced, we know that oxygen is not it. The oxygen didn't change at all. The ones that did change, the carbon went from +2 to +4, and the chlorine went from +1 to 0. So carbon got more positive. Getting more positive means you would have to lose negatives, lose electrons. The loss of electrons is oxidation. Good old Leoger. So carbon lost electrons. It is the thing that was oxidized. Chlorine got more negative, +1 to 0. It got less positive or more negative. Gain of electrons is reduction. So chlorine is the thing reduced. And so this is where a lot of you kind of made mistakes in the Chapter 8 quiz, because you tried to overcomplicate the oxidation and reduction processes. Oxidation and reduction do not occur to the reactants. They occur to the elements within the reactants. However, when we are asking about oxidizing agents and reducing agents, those are related to reactants, not individual elements. And it's a crisscrossy kind of thing. The element that was oxidized is part of the reducing agent. So since the carbon was oxidized, the reducing agent is carbon monoxide. The chlorine was reduced, so that means that the oxidizing agent be the reactant containing chlorine, that'd be the hypochlorite ion. Duncan. Yeah, because we have to understand what it means to be an agent. So an agent in this case indicates we have a reactant that is forcing some kind of action. So the oxidizing agent is forcing oxidation, which means it itself isn't being oxidized, it's forcing something else to become oxidized. And the reducing agent isn't being reduced itself, it's forcing something else to become reduced. And so that's why if we properly identify the elements that are getting oxidized and reduced, we can flip them when it comes to identifying the correct agents. Because we're identifying what the substance does, not what the substance has done to it. So it's kind of backwards logic, because you would think that we would just use the same term for both. But it's really about the action that it performs, not what happens to it. All right, we've got time for a couple more questions. What else do we want to talk about? Number two. So the equations. All right. All right, so once again, we're looking at ionic and net ionic equations. We are also looking at balancing concepts. So before we do anything else, we want to make sure that we have these things balanced. So for the first one, balancing it is just a matter of doubling the base and doubling the water output. Now it comes time for those solubility rules to become important. And so, again, one of the reasons we hammered that idea of the solubility rules and solubility rules proficiency coming into this exam was because you need those skills to do these kinds of problems. And actually, if you look at the last two proficiencies that are on the list, the one that we're doing next Friday is oxidation numbers. The one the Friday after that, ionic equations, kind of bringing everything together. So those are the last two. We've saved those for last because they're kind of the most difficult concepts to kind of bring out and bring together here. So the thing to do now that we've balanced it, is we have to identify, put each of these compounds into one of those 6 categories: acid-base salt, soluble, insoluble, strong, weak. So here's where our identification really helps us out. I should be able to look at this formula here, H2SO3, and immediately identify that this is an acid. That's an acid. OH here is a base. This is neither acid nor base. It's a salt. And water isn't a salt either. We're just going to call it a non-electrolyte. So we know what we'll do with that when the time's right. Now, we can't just simply stop at acid, base, and salt, because depending upon the nature of those acid, bases, and salts, that's going to dictate whether these break apart or stay together in the ionic equation. H2SO3, sulfurous acid, is not one of those 6 strong acids. Remember, the 6 strong acids: hydrochloric, hydrobromic, hydroiodic, chloric, sulfuric, and nitric. And perchloric, if you want to get technical, there are usually 7. We just don't always address all 7. If it's not one of those, it's a weak acid. So weak acid would be the correct designation here. Potassium hydroxide, I know we don't have a periodic table in this room, but I think you can take it on pretty good authority that potassium is an alkali metal. It's in group 1, and all of your group 1 hydroxides are strong bases. So that's a strong base. As far as this as a salt is concerned, well, it's a potassium salt. All potassium salts dissolve in water. So we can mark that as soluble. Now that we've got all 4 of the compounds classified, now we go through the process of breaking them apart if they get broken apart. And remember, it's only the strong acids, strong bases, and soluble salts. So if the marking begins with an S, then we know to break it apart. If it doesn't, we know to keep it together. So weak acid stays together. Strong base breaks apart. And we got to make sure that we keep the coefficients with it. So this is going to be 2 potassium ions and 2 hydroxide ions. Potassium sulfite breaks apart. Remember, potassium ion is K+. This 2 just becomes the coefficient now instead of the subscript. Sulfite ion is SO3 -2. And water, since it is a non-electrolyte, stays together. We can almost think of it as it is so weak of an acid or weak as a base that it doesn't break apart at all. It's not technically true, but the degree of breaking apart is so minuscule that we won't worry about it until Chem 106. So that's the total ionic equation. All that we need to do to turn the total into net is cross out anything that is common to both ends, which in this case would just be the potassium ions. So the net ionic would be the sulfurous acid reacting with the 2 hydroxides to make the sulfite ion and 2 waters. Questions on the first part of this? All right, let's move on to the second part. Now, for balancing purposes, I'm going to use one of my favoriteest tricks. Here I've got a multi-subscripted chemical compound. I'm going to use those subscripts to turn them into coefficients on the other side. That should make the balancing easier. So 3 bariums in barium phosphate means 3 barium chlorides. 2 phosphates in barium phosphate means 2 ammonium phosphates. If I put that together, I have 6 ammonium and 6 chloride, so 6 ammonia chloride. So there's the balancing part. Now, we can look at this directly and see we've got no acid or base in this second example. We've got no hydrogens, we've got no hydroxides. All of these are salts. So now we just got to put them into the right categories, soluble or insoluble. Ammonium compounds are always soluble. So the ammonium phosphate is soluble and the ammonium chloride is soluble. Now we're just left looking at barium chloride and barium phosphate. Chlorides are usually soluble. The only ones that are not are the Merle's chlorides. Remember, Merle's chlorides, mercury, lead, silver, strontium. Barium's not any of those. So it's soluble as well. I said strontium, that's not correct. Mercury, lead, silver. Those are the only 3. Barium phosphate. Phosphates are usually insoluble. The only exceptions are the group 1s and ammonium. Barium is not in group 1, it's in group 2. And barium is not ammonium, so this one is insoluble. Since again, we're dealing with salts here, it's just a matter of breaking apart the ones that break apart, keeping together the ones that stay together. 2 times 3 would give me 6 ammonium ions. 2 times 1 would give me 2 phosphate ions. 3 barium ions and 6 chloride ions. On the other side, barium phosphate is insoluble, so it will stay together. And the ammonium chloride, remember the 6 is going to carry over both. 6 ammonium ions and 6 chloride ions. To turn the total into a net, we need to cross out all the common factors. The 6 ammoniums cancel. The 6 chlorides cancel. All that is left are the phosphate ions reacting with the barium ions to make barium phosphate. So a lot goes into a total and net ionic equation. You've got to know how to balance. You've got to know your solubility rules. You got to know how to interpret the results of those solubility rules to make the correct total ionic equation. And usually, if you can make the correct total ionic equation, getting the net ionic equation is no big deal, because you just shake out whatever's common, whatever's redundant. I would say we have time for one more question. I give you a chance to ask me any questions about this one if you have them first. All right. Anything else anybody wants to go over? Okay. Okay. This is another retread from the quiz. The density of a 2 molar hydrochloric acid solution is 1.16 grams per milliliter. What is the percent mass for hydrogen chloride in that solution? Okay, the important things to remember. This is a concentration. This is not. I think the biggest mistake that more people made on Tuesday was confusing density for concentration and trying to turn that 1.16 grams per milliliter into moles per liters and completely forgetting about that 2 liters or that 2 molar. We have to remember what things are. This describes the solution. This describes hydrogen chloride in that solution. So we are going to use both components, but we can't use them interchangeably. They each serve a purpose. So let's start with our 2 molar solution. So that means that we have 2 moles of hydrogen chloride in every 1 liter of solution. That is the definition of molarity. Now, to turn this into mass percent, we need to convert this into grams of hydrochloric acid divided by grams of solution, and then we'll take that value and multiply it by 100%. That's what we have to do. So we can kind of think about this. This is 2 separate sets of conversions. I need to turn the moles into grams, and I need to turn the volume of the solution into grams as well. And so it'll be easier for you to wrap your head around if you treat them separately and then bring them together at the very end to do the calculation of the percent concentration. And so if I keep that in mind, 2 moles of HCl, every mole of HCl weighs 36.46 grams. 2 times 36.46 is 72.92 grams. For the bottom conversion, 1 liter of solution. 1 liter of solution. Every liter has 1,000 milliliters in it. And here's where the density becomes important. Notice we're staying just in the solution lane here. We haven't done anything with HCl. We're just looking at the solution. That's where the density is important to us, when we're staying in just the solution lane. Every milliliter is 1.16 grams. So 1,000 times 1.16, 1,160 grams of solution. So if I put those 2 values into my equation, 72.92 grams of HCl divided by 1,160 grams of solution, and I multiply that by 100%, I would get to 3 significant figures, because there are only 3 in the denominator here, 6.29% HCl. So my caution to all of you when these kinds of questions come up is really to avoid overcomplicating them. Separate it. Know your definitions, separate it into two smaller calculations that eventually you're going to put together. And if you have to go the other way, if you start with that 6.29%, again, separate it. I've got 6.29 grams of HCl in 100 grams of solution. I turn the 6.29 grams into moles. I turn the 100 grams of solution into milliliters and into liters, and I put it back together to figure out the molarity. I think the problem a lot of you ran into on Tuesday is that you tried to do it all in one easy calculation. And you started to lose track of where each of the numbers went and where each of them belonged. So if I leave you with kind of a closing thought there, that's it. None of the calculations that you're going to be asked to do are terribly complicated calculations. They might be long, but they're not going to be these, massive, I can do it all in one series of long calculation conversion kinds of things. The longest conversion you have to do is 3, maybe 4 steps. Now you might have to do multiples of that, but you shouldn't be seeing dimensional analysis that's, 6, 7 cars long. Right. One last note I'd make for you here, just kind of a common sense note. As you're studying tonight, set your alarm clock in some kind of way and put an end to your study at a particular time. Especially for those of you in the 9 o'clock section, I don't need a bunch of zombies trying to take my test. Pulling an all-nighter, trying to study all day, it's not going to work for you. You're going to do way better with sleep than you're going to do without it. So set your alarm. Say, I'm going to be done by 11 o'clock. I'm going to be done by 10:30. Pick a time that is right for you and put it away. Come back to it in the morning if you want to, but make sure that you get yourself the proper rest, because you're going to need all of your neurons firing and all firing correctly if you want to do your best. Have a good evening.